Hi, this is Abhijit from DDRA. Welcome to this first video from our series Quick Embedded, where I explain some simple embedded concepts in less than 5 minutes. So today we will be talking about switch bouncing. To demonstrate what that is, I have a board here with me with two tactile switches. I'll be using this one, and I also have a simple program that I've written to count the number of switch presses that I make on this board. So I am using an STM32 Nucleo board for this program, and I'm using STM32 Cube IDE to program the board. So this is the program that I've written. It's a very simple program which polls the current state of the GPIO pin. I have initialized the current and previous state variables to high. As this polls, every time there is a state change, we check for a rising edge. Every time there is a rising edge, I simply increment the counter called switch press count, and I use UART transmission to transmit the number of switch presses onto my serial terminal. So this switch is pulled up, which means the controller reaches a high state when the switch is not pressed, when the switch is open. When the switch closes by depressing it, it connects the GPIO pin to the ground, so the controller reads a 0 or a low state. Now, let me press the switch a few times and check the number on my serial emulator. As you can see, the actual number of switch presses do not correlate with what we have seen on the screen. We see a few more presses registered than actual. So, what is happening? This is due to a phenomenon called as switch bouncing. This is an effect produced by a combination of multiple factors in mechanical switches, due to which we see oscillations between high and low TTL states. Usually, it is in the order of a few milliseconds. Due to the nature of the making and breaking of the mechanical contacts, the imperfection in shape and size of the contacts, and the springs in the switches, we see multiple changes in the states of the pin. I can test this with my picoscope. I am using TinyLab for my hardware and Pico 7 software for capturing the waveforms. As I press the switch, you can see the bouncing being captured very clearly. So, I can see two rising edges here with a delta of 336 microseconds. This leads the controller to accidentally capture two edges. A simple delay of 50 milliseconds is more than enough to debounce most switches. However, due to the quality of these particular switches, I'll be using a delay of around 200 milliseconds. Note that this is blocking code and will affect the performance of high-speed applications. I am flashing the controller now, and let us now see the results of a debouncing code. As you can see, there are no unnecessary switch presses that are being registered as a result of the debouncing code. If you find this video useful, click on like and type quick in the comments to encourage us in doing more such videos. Note that there are better ways to implement debounce, and non-blocking elegant code is easy to implement. We will explore these methods in a future video. Till then, happy learning.